In this demonstration, we will use a reciprocating saw as we see how Fusion 360 can be used to improve an engineering team's product development process. Usually, while a product is developed through concept to design to manufacturing, several tools are used to complete the design. Unfortunately, this usually causes translation issues, and updating a design during the development process does not update from tool to tool. Why wouldn't you expect a greater level of integration from the tools you stake your professional reputation on? Design changes get more complicated and costly the further the design is in the product development process. Fusion 360 is the product innovation platform which streamlines the product development process, helping design changes propagate to related data that are created at different stages of the design process. To start, while designing, usually a tool is used to create complex surfacing, then another tool is used to add parametric features, then another tool is used to make direct modeling changes. Fusion 360 is a surface, parametric, freeform, and direct modeler all in one package. We will start by demonstrating these different modeling techniques by designing components for a reciprocating saw. We will start with the design of the plastic housing of the reciprocating saw right after our engineering team has finished modeling and designing the internal package. Our goal is to model this housing as tightly as we can to this internal package. So let's jump into the freeform environment, which is powered by T-splines technology. One of our industrial designers created a concept sketch in Sketchbook for us to use as a starting point for modeling our plastic housing around. We can resize this image to the appropriate size, but this PNG file used for the image does not have units. I can calibrate this image using a known measurement to better approximate the size of this image. Once the image is in place, we can start creating a T-spline body. We will use a face to start our design. Let's manipulate the face to the outside of this internal package in order to make sure we do not have any interferences. Now that we have the face in a non-interfering location, we can hide the internal package as we start to mold our body. I have one face to work with now, so let's add a few faces. As I add faces, I am changing the direction that I drag the triad to get the shape I am looking for in my plastic housing. With the triad, I can move and scale faces, edges, and vertices in the direction I prefer. Usually to create complex shapes like this in a traditional CAD tool, I would have to create many sketch planes and sketch profiles. Then I would have to fight between the transitions between different bodies. Now let's add a new body using a cylinder. This body starts with 4 faces along the length of the cylinder. One of the best practices with T-splines is to start with a coarse mesh, then add complexity in areas of high detail. I can specify a specific size for the cylinder, or in this case manipulate the new body to fit the concept sketch. Now I'm going to start to make the transition between these two bodies. On my original body, I need to add an edge. Doing this creates a T-junction on this face, which is where the T in T-splines comes from. This is a patented technology which is seen in Fusion 360. Now I can manually merge these two bodies, but rather I will let Fusion 360 merge the two bodies with a bridge. Once the two bodies are merged, I can still manipulate this body just as before to get my desired results. In traditional CAD, I would be changing sketches, waiting for the CAD tool to solve the tricky loft or sweep, then hoping it didn't break any other feature. I will continue to use the same procedure on the top of this handle to get the desired transition. As the cylinder needs to navigate around this curve, I could rotate the edge loop to better match the curve. Again, I will add edges in areas of high detail when required. Now let's take these edges and add a few faces. Notice I get a seam where these edges overlap. I can weld these vertices together to get one continuous body. The entire time, Fusion 360 is maintaining the curvature continuous nature of this surface body. Up until this point, I have been working on half of the plastic housing. The housing is going to be symmetric about the left and right side of the internal assembly. I do not have a clear plane to mirror this body smoothly because I haven't been moving the vertexes to a specific plane. With Fusion 360, I can flatten edge loops to a specific plane. This will help when I mirror because I will get the option to weld the mirrored body to the original. Once the body is mirrored, I get a green line for the symmetric plane. If I manipulate one side, the exact change will be propagated to the other side. Don't worry, I could turn on and off symmetry when convenient. The reciprocating saw is going to have to rest once set down on a flat surface. So we can take these bottom vertices and flatten them to create a flat portion for this body. I've come to a point where I could test out a few different design ideas on the handle. I can quickly copy and paste the freeform body. Now I could test out a few different concepts on the handle. Imagine how many sketches and features I would have to recreate, or how many different files I would have to copy and manage. In Fusion 360, we can iterate on many concepts to ensure we get to the best concept quickly. In this case, I'm not the decision maker on the handle concept. From within Fusion 360, I could send a comment out to my design team to get feedback on which handle to run with on this design. Once I exit the freeform workspace, Fusion 360 automatically trans this subdivisional model into a NURB surface. A freeform feature is recorded in the timeline which can be edited at any point in the design process. Editing the freeform feature will throw me right back into this environment where I can start manipulating this freeform surface again. Let's skip ahead in the design process. Now that we are done creating our freeform surface, we will start by adding parametric features on the B side of this plastic housing. Usually this process is done in a completely different tool, which would require a translation. This means that updates to the surface do not propagate to the tool creating the parametric bosses, ribs, and cuts. In Fusion 360, we will demonstrate how these two separate modeling techniques can integrate broken product development workflows. Let's use a selection set to hide the internal components in this assembly. We want to start creating the cutouts for the vents so the internal components don't overheat. While sketching, we can type the dimensions out to define the sketch entity while being created. This will automatically add dimensions that can be changed later if needed. Then using inferencing, we can finish this parallelogram and automatically make the parallel relationships with the already existing sketch entities. Now all the vents will be the same size, so we can pattern the vents horizontally. Then we can repeat the last command by dragging up, which will enable the pattern of the sketch entities along a certain direction. I want to skip a few instances of this pattern, so I will uncheck the boxes of the instances I do not want in this sketch. Now let's cut the vents into the housing. In the same extrude feature, we can choose to add, subtract, or intersect with geometry, or add a new body or component. Fusion 360 gives us the flexibility to have what would usually be multiple features all in one tool. Next, we will work on adding a few ribs to give this plastic housing strength while in use. Let's sketch a few lines where we want the ribs to be located. When the web tool is used, Fusion 360 will automatically extend the ribs to the extending boundary at a specified thickness. Next, we will need to cut through the ribs where they would interfere with the internal assembly. Let's sketch a rectangle on the front rib and add a few dimensions. We will use an extrude cut and use the to extents to specify a distance to terminate this cut. If the distance of the ribs ever change, the cut will always go through all three ribs. Let's add a fillet to all of these ribs. We will use a ruled fillet. The ruled fillet does what it says, adds fillets based off of rules. If a rib is added to the web feature, the rib will automatically be filleted with the same parameters. Next, we will start to add the overmolding for the front gripping portion. We will start by splitting the faces in order to create the area where we want to add a 1.5mm offset. When learning a new UI, it's difficult to remember where all the commands in Fusion 360 are located. I will use the command search to locate the split face command. We make it easy to locate commands so you could keep your mind on the design. Then I'll use the paint selection to select the faces to be split by simply dragging over them. To create this overmolding in other tools, I would have had to copy the surface, thicken the surface, then combine it back to the original body to get my overmolding. Instead, I'm going to use the command for all commands, press pull. When I select faces, press pull will turn into offset faces, and this will allow me to place my desired 1.5mm offset to the body. When I select an edge, press pull will turn into a fillet. This tool will change depending on what is selected, and helps design faster rather than searching for the correct command. Let's repeat the process to split the back handle portion. Instead of using the split face to add overmolding, the split face can also be used to specify certain faces where we want a specific appearance. One of the requirements of this project is to create some photorealistic renderings for our marketing team. Once the faces are split, we can apply different appearances to the front and back gripping portions. We will come back to create a render of our design later, but now let's worry about assembling our product. Fusion 360 does not require the planning of assemblies early in the design process. Bodies, components, and assemblies can all live in the same design. Bodies can be turned into components when convenient in the design process. The main reasons to turn bodies into components is to allow assembly motion or when creating bill of materials. In this case, the housing will remain fixed in our assembly, so we will ground it to lock it down. In this case, we will start assembling the reciprocating saw to allow the correct assembly motion. Now, these internal components were designed using the top-down design approach, which means they were designed in context of each other. Rather than pulling them apart to reassemble them with mates or constraints, we can use as-built joints. As-built joints will define the relationship between components based off mechanical motion rather than face-to-face, edge-to-edge, and vertex-to-vertex interaction. Simply select the two components, then the point they will pivot around, and then you're already on the next set of components. In traditional CAD, when mating or applying constraints, usually an engineer is trying to lock down the 6 degrees of freedom, 3 translation, and 3 rotation. This usually takes 2 to 3 constraints or mates to get the desired motion. In Fusion 360, we apply one joint. We lock all 6 degrees of freedom down and change the joint type to get the desired assembly motion. This will help designs get assembled faster and behave more robustly when design changes are made. Now, I need to add some hardware into this design. Rather than creating and maintaining a library of common hardware that I would order from common suppliers, Fusion 360 has partnered with standard part catalogs such as a MasterCar in this example. Here we can browse or search for our part and insert it directly into Fusion 360 without having to take an extra step of downloading a 3D file and translating it into my database. This will prevent our team from having to maintain ever-changing part libraries. Once in Fusion, these components are just like any other component. In this example, we can pattern the screws to the other holes, and of course, I would get 4 of these machine screws in my bill of materials. Here is the cool part. I have created that freeform shell for the plastic housing. Then I made some parametric features for the mounting bosses, ribs, cuts, and overmolding. Usually when a design change is required to the freeform surface created early in the design process, multiple changes are required between multiple tools. Usually when a design change is required to the freeform surface created early in the design process, multiple changes are required between multiple tools. In Fusion 360's integrated toolset, when I make a design change to the surface, the downstream features will update accordingly. No need to recreate surfaces or fix a bunch of red and yellow features in the feature tree. This will save both time and money and hours of rework for a design change anywhere in the design process. Now we will need to analyze this assembly to ensure that it survives a 75-pound load while in use. Using Fusion 360, we can create a finite element analysis to test linear static, modal frequency, thermal, and thermal stress scenarios. we can simplify our analysis by focusing on the interaction of a few components. Let's fix these faces where the gear housing will be attached to the plastic housing. Next, we will apply a 75-pound load to the bottom face where the blade holder will come in contact while in use. One of the most common mistakes while setting up a finite element analysis is either over or under constraining our problem. Fusion 360 allows us to turn on our degree of freedom plot. This will show if components are fully fixed or free to move. Now, we will need to add contacts. Contacts are used to describe how components interact with each other. In this case, I'm going to use an automatic contact. I have told Fusion 360 to look for faces within a 0.1 mm tolerance and to make a bonded contact. The last thing we need to do before solving is to change the mesh. Here, we can make it a finer mesh and turn on a second order tetrahedral element because we are solving for stresses in this scenario. So let's solve and let Fusion 360 analyze this design. Normally, we would want to ensure that our simulation converges on a stress value. In that case, I would turn on our mesh adaptation tools, which will refine our mesh in areas of high stress concentration. Now that Fusion 360 has solved our simulation, we can interrogate our results by looking at different plots, such as safety factor, stress, and displacement. In addition, we can use tools such as surface probes, slicing planes, and animations to see how stress is distributed through design as the 75-pound force is applied. Unfortunately, this analysis did not meet our design requirements for a factor of safety above 1. So let's make some design changes to the gear housing to ensure it can withstand our loading scenario. We will open up the gear housing, which is referenced into another design file. This file was imported from a different CAD system. There are no features for me to parametrically edit to make design changes. Fusion 360 has direct modeling tools to aid in making changes to dumb geometry. We can increase the length of this frontal portion and the width by simply selecting the face and dragging it. Fusion 360 will heal the fillets and curves to the correct location. While I have this file open, I have noticed some other unwanted features that would be difficult to fix without parametric features. In this case, I can select the text and delete it by just simply hitting the delete key. Fusion 360 will automatically heal back the text to the flat face. Also, this blend in the pocket is not intended in our design. We can select all the faces in the blend and hit the delete key again, and Fusion 360 will heal back the edge. If required, I can reapply a fillet to get a better blend for that curve. Finally, we have a sliver face over here. These are sometimes tricky to fix, but again in Fusion 360 we can select it and hit the delete key. Now we have 2 ribs in the back of this housing, where only one is required in the middle. I can simply select one of the ribs and delete it. Then I could use our move tool to select the remaining rib and move it into the correct location simply by rotating the triad. Usually, to make these changes in a purely parametric tool, it would require a lot of sketching and extruding over existing geometry. Those tactics are not a best practice and cause issues when design changes occur. Now we will save and create a new version of our gear housing. Let's switch over to the top level assembly. Whoa, you might notice my changes to the gear housing did not propagate into this assembly. Why hasn't it updated? Well, in Fusion 360 we don't automatically update the reference to the latest version. In other tools, sometimes bad design changes are made and they are propagated to the top level assembly. We allow the user to choose when to update to the current version. In addition, we can always choose an older version, just in case the changes I made would cause errors. This will prevent design teams from having to fix red and yellow assembly trees from unwanted changes to the top level assembly. Versioning is inherently built into Fusion 360 and doesn't require a complex PDM system to implement. Now that we have the updated gear housing in our assembly, let's jump back into the simulation to ensure the design changes made will increase the factor of safety of our design. Having an integrated toolset allows us to jump back into any workspace and save time on rework from design changes. In this simulation workspace, the setup is already complete. We just need to rerun the study to analyze our new design concepts. Rather than resetting up simulation studies, we can test different design ideas and simply resolve them to make sure we get to the best concept early in the design process. Now that we are sure that our design will last the prescribed load, we can start by creating a photorealistic rendering for our marketing team. Let's switch to the rendering workspace. We will start off by applying a textured plastic appearance to the trigger. We can browse for a material in Fusion 360's customizable appearance library. Here we can change the scene and scene settings, such as applying depth of field to this image. Let's change the lighting of this image by changing the environment. Finally, I could turn on the ray tracing to leverage my computer's hardware to calculate the light bounces in this image. Unfortunately, I need to continue designing this reciprocating saw. While this image is being rendered, it is using up a majority of my computer's resources. Instead, I could start a cloud render. This will leverage the nearly infinite resources of cloud computing. I can specify a few parameters, and in a few minutes Fusion 360 will return a render without having to stall my design team from leveraging their computer's hardware. With the cloud rendering option, we can quickly queue up several images with slight differences to test out different rendering scenarios. While that image is being rendered, let's check out the design in A360. A360 is another access point to your Fusion 360 data in a web browser. A360 is an essential part for a design team to work together and understand how different design data is related. It is also a great tool for non-CAD personnel to collaborate throughout the design process. In a web browser, I can see what design my file is referencing. A360 also displays the related data created during the design process in other workspaces, such as CAM, animations, renderings, and simulation results. Right in a web browser, we can jump into an immersive experience and view the FEA analysis we created with Fusion 360 a few minutes ago. In addition, I can jump into the design and interrogate the assembly tree and see which components this design uses, such as what type of fasteners I chose to use for the internal assembly. Let's open up the commenting pane. Here we can see different comments that have been made throughout the design process. Usually these are key design decisions made between multiple stakeholders' email boxes. Now I have a centralized location for all design decisions made throughout the design process that can be audited for when and why decisions were made. Next, we can redline our design right in a web browser to better illustrate required design changes. Gone are the days where we would try to describe with text what we want to change in the design. In addition to redlining, we can create comments on points or objects. These will produce a balloon referencing the selected entity to better illustrate what needs to be changed. Of course, any of these comments can be seen in Fusion 360 as well. No matter where you are, an engineer can hop on a web browser and still collaborate on key design decisions that need to be made throughout the design process. Now, I need to send a file to a partner for them to start some post-processing work. I can start by sharing a link. Here I could give them access to download the file or password protect the link. Once they click the link, they will see the design in a web browser. Here they can choose which file format works best for their post-processing tools. There is no need to download a viewer, worry about file compatibility, or send them the wrong file type. This shared link changes the way design teams will work with external stakeholders. Of course, I can close the link to stop access to the file if I no longer want to share my design with the external stakeholder. Throughout this demonstration, we have seen how we can have multiple designers, engineers, managers, and external stakeholders collaborate on a design. We have also seen how Fusion 360 integrates different modeling techniques such as freeform, parametric, surface, and direct modeling all in one package. Now we will demonstrate how Fusion 360 integrates post-processes such as simulation, CAM, rendering, and animations. These post-processes will update accordingly from design changes made throughout the design process, which will reduce the amount of rework required to set up these processes. Now, our next task is to program our part to machine on our Haas mill. Let's open up the parent assembly. We can find where this saw is being used in other assemblies. Let's open the core of the injection mold in Fusion 360 to throw some toolpaths on. We can start by creating our first setup. We will orient the Z-axis and pick the location for the pickup of our part. We will use this corner to probe when locating our part in our machine. Normally we'd want to take this time to measure our stock with calipers, and we can input these values on the stock tab to ensure our part is cut to the correct dimensions. Next, let's start roughing out the core with a 3D adaptive clearing toolpath. Adaptive clearing is a roughing strategy available for clearing large quantities of material effectively. It is unique in that it guarantees a maximum tool load at all stages of the machining cycle. Our roughing tool will ensure that the wear is uniform across the length of the tool. After, we will throw a parallel toolpath as a finishing pass on the contoured surface. Let's first pick a tool, then pick the boundaries where we want the toolpath to machine over. Finally, let's ensure that we don't crash our tool by simulating our toolpaths. Simulating our toolpaths ensures that our parts are being cut correctly and we don't make any costly mistakes such as running the part into a vise. We can use the timeline at the bottom to jump to different points in the simulation to interrogate how our machine will be cutting our part. Now a call has come from the customer that they would like to change the surface of this plastic housing for the reciprocating saw. In a typical product development process, this type of request would cause a lot of rework and a lot of money to discover at this point in the design process, especially if we cut steel for the mold already. Instead, in Fusion 360's integrated toolset, we can go back and edit the freeform feature in the reciprocating saw design. Here we can use the press-pull gestures to manipulate the shape of our housing. In a traditional CAD tool, I would be changing sketches and lofts, hoping it doesn't break any of the transitions between features. Then when I get back to the design where the mold is referencing the component, we can update the assembly. This will update with the changes made from manipulating the freeform surface. Once the change has been made, we can generate the toolpaths again. This will prevent us from having to reset up all my toolpaths again. To ensure that our tool will cut the updated design, we can simulate the CAM toolpaths, and of course I can post this out again to send to my machine to start cutting parts with the new design changes. Next, let's start drilling these holes. We will select the size of our drill, then we can select a face of the hole. Then Fusion 360 will select all the remaining same size holes. This will help program parts quicker rather than searching for all the same size holes. Now let's switch over to the modeling workspace. Sometimes programmers or machinists need to make last-minute changes to the part being cut. Rather than hunting through sketches and features to make changes to a part that someone else designed, they can switch to a direct modeling environment. Now we need some input on a design change from some external stakeholders. From Fusion 360, I can start a live review session. This will generate a link which I can copy and paste into an email. Once my external stakeholder receives the email, they can click on the link and open it up in a web browser. An interactive web experience will be open in their web browser where they can collaborate on design changes. Here I can choose the driver and make design changes. In real time, the design changes are propagated to their session. I can make some changes requested by the customer to make sure I make an approved change. I can use some of the direct modeling tools to manipulate this hole away from the cut in the mold. In addition, I can choose to make them the presenter. They can collaborate on what needs to be changed from a web browser anywhere in the world. This will truly change the way design teams collaborate with both internal and external stakeholders. Throughout this demonstration, we've shown you how Fusion 360 has integrated different modeling techniques such as surfacing, freeform, parametric, and direct modeling. Also, Fusion 360 integrates different post-processes such as renderings, animations, simulation, and CAM toolpaths. These different types of integrations ensure that if a design change is made anywhere in the design process, downstream data also reflects these changes. This will ensure that design teams will save time instead of rework. Also, we have leveraged the cloud to collaborate with our design team. We were able to create comments and red lines which illustrate key design decisions. These comments travel with the file and produce an auditable trail of when and why decisions were made. Also, we were able to stay connected to our data via a web browser or the Fusion 360 mobile app, which is available for iOS or Android. Finally, we have given access to a variety of tools such as high-end design, visualization, documentation, simulation, and manufacturing tools. Usually these are different tools which each have an expensive price point and subscription cost. Fusion 360 is constantly being updated. Make sure to check out our roadmap to see what we will be bringing into the tool next, or go visit the Idea Station to contribute different ideas that could be implemented into Fusion 360.